Let us begin slowly, and let us also begin with a why view. Calculus, at its core, is a way of talking carefully about change and about accumulation. Change is what we later study under the name derivative. Accumulation is what we later study under the name integral. Those two themes will come back again and again, and it is worth repeating them right away. Calculus is the mathematics of how things vary, and also the mathematics of how small contributions add up into a total. There are two master ideas that guide much of what we do. The first is the idea of zooming in. When we zoom in closely enough on a nice curve, it starts to look almost straight. In other words, on a very small scale, complicated behavior often becomes simple, and the simple behavior is essentially linear behavior. The second master idea is the idea of adding up. If a quantity is built from many small pieces, then we try to understand the total by understanding the pieces and then combining them. So we will come back to these ideas in cycles, zooming in to simplify, and adding up to build a whole. It is worth pausing and reflecting on why these two ideas are so powerful. The world, whether physical, economic, or biological, often presents us with relationships that are too complicated to capture in one direct step. But if we can understand what happens over tiny changes, and if we can understand how tiny pieces contribute to a total, then we can rebuild a large understanding from small, manageable insights. This is a steady rhythm of calculus. Now, before we can speak precisely about change or accumulation, we need a language for describing relationships between quantities. That language is the language of functions. So we will spend time treating functions not merely as rules for computation, but as objects we can study, compare, transform, and reason about. A function, in the most practical sense, is a relationship that takes an input and produces an output. But it is worth repeating in a more careful way. A function is an assignment that associates to each allowed input exactly one output. That phrase allowed input is important. The collection of all inputs we permit is called the domain. The collection of all outputs we actually obtain is called the range. Sometimes people also say codomain, which is a declared set of possible outputs, but for our purposes the range is the set of outputs that genuinely appear. Let us pause and reflect. When you are given a function, you are not only given a way to compute. You are given a whole structure, a set of possible inputs, a rule that chooses an output for each input, and therefore a set of outputs that can occur. The domain tells you what questions you are allowed to ask. The range tells you what answers you can actually receive. It is worth repeating this in a slightly different way. A function is like a machine, but it is also like a promise. The promise is that every input in the domain gets a well-defined output, and never two different outputs. This promise is what lets us reason safely, because ambiguity is removed. Now, one of the most important ways to understand a function is through its graph. The graph is the picture that shows, for each input, where the output lies. Even if we avoid symbolic notation, we can still speak about the graph as a set of points in the plane where the horizontal coordinate is the input and the vertical coordinate is the output. The graph is not merely a drawing. It is a geometric object that encodes a function's behavior. Let us pause and reflect again. A function can be represented in many ways, by a formula, by a table of values, by a graph, by a verbal description, or by data from an experiment. Calculus will often require us to move gently among these representations, because each highlights different features. The graph emphasizes shape and behavior. A table emphasizes local values and patterns. A formula emphasizes exactness and algebraic structure. Now we should speak about transformations. When we take a function and modify it, we often do so in predictable geometric ways. For example, shifting the input values corresponds to moving the graph left or right. Shifting the output values corresponds to moving the graph up or down. Stretching inputs corresponds to squeezing or widening the graph horizontally, and stretching outputs corresponds to expanding or compressing the graph vertically. It is worth repeating what is happening here. We are learning to treat a function as an object that can be manipulated. We can take a basic function and, by shifting, scaling, reflecting, or combining, create new functions. This is not just an artistic exercise. It is a way of building complicated models from simple pieces. We should also mention inverse functions, because they are a natural question once we think of a function as a mapping from inputs to outputs. The inverse function, when it exists, reverses the relationship. It takes an output value and returns the input value that produced it. But here we must be careful, and it is worth stating the condition slowly. An inverse function exists only when the original function never sends two different inputs to the same output. If it did, then the inverse would not know which input to choose. So the existence of an inverse is really a statement about uniqueness. Outputs correspond to inputs in a one-to-one way. Let us pause and reflect. Inverse functions are not guaranteed. They exist when the function is, in an intuitive sense, reversible. And that reversibility has a geometric meaning, a graph that passes a certain horizontal line test, meaning no horizontal line meets the graph more than once. We will return to this idea later, because it connects to monotonic behavior, to solving equations, and to logarithms as inverses of exponentials. Before we proceed, let us summarize what we have established. We have said that calculus studies change and accumulation. We have said that functions give us the language for describing relationships. We have emphasized domain and range, and we have noted that the graph is a geometric encoding of the function. We have introduced transformations and the idea that functions can be treated as objects that we can modify. And we have introduced inverse functions as reversals that exist only under a uniqueness condition. Now we will slowly move to the families of functions that appear so often that it is helpful to recognize them by their typical shapes and behaviors. It is worth repeating, in calculus, we do not only compute, we also develop intuition about how functions behave. And a large part of that intuition comes from knowing the basic families. First, there are polynomial functions. These are built from sums of powers of the input multiplied by constants. Their graphs tend to be smooth, without breaks or sudden jumps, and their long-term behavior is dominated by the highest power. They are often used as approximations because they are algebraically simple and behave nicely under differentiation. Next, there are rational functions, which are ratios of polynomials. These behave like polynomials in many places, but they can also have special features where the denominator becomes zero. Near such points, the function may blow up, meaning the outputs grow without bound, or the function may fail to be defined at all. Rational functions therefore teach us to pay attention to domain and to behavior near a problematic point. Then there are trigonometric functions, such as sine and cosine, which capture periodic behavior. Their essential feature is repetition over regular intervals. They model waves, cycles, oscillations, and rotations. They are smooth, and their regularity makes them a central source of examples and applications. Then there are exponential functions, which represent growth or decay where the rate of change is proportional to the current value. Exponential growth is the kind of growth that accelerates as the quantity grows. Exponential decay is the kind of decay where a fixed percentage is lost per unit time. Exponential functions are distinguished by their strong long-term behavior. They can grow very rapidly, and they appear naturally in many differential models. Finally, there are logarithmic functions, which are inverses of exponentials when we restrict the exponential appropriately. Logarithms convert multiplication like growth into addition like growth, and they grow slowly. They are essential in understanding scales, orders of magnitude, and multiplicative processes. Let us pause and reflect on why we list these families. Calculus is full of questions like, what happens near a point, what happens far away, how does the function respond to small input changes, and how does it accumulate area or total effect? Different families answer those questions in different characteristic ways. So knowing these families is like knowing the main characters in a story you're about to read. It is also worth repeating that these families can be combined. We can add them, multiply them, compose them, and transform them. Often a complicated function is best understood as a combination of simpler behaviors. And this brings us gently to the next concept, limits, which allow us to describe behavior without requiring exact equality at a point. Now we come to limits, which are one of the most delicate and foundational ideas in calculus. A limit is a way of describing what a function is approaching when the input gets close to a particular value. The key phrase here is it gets close. We are not necessarily asking what happens at the point itself. We are asking what happens near the point. We are asking about a tendency, not a direct evaluation. It is worth repeating, because many early confusions come from forgetting this. A limit is not the same as a plugging in. Plugging in is evaluation at a point. A limit is behavior near the point. Sometimes they agree, and when they do, life feels simple. But sometimes they do not agree, and then limits reveal more structure than direct evaluation. Let us pause and reflect with a calm image. Imagine walking along the graph of a function as you move your input closer and closer to a target value. You might not be able to stand exactly on the target input, perhaps because the function is not defined there. But you can still walk closer and observe where the output values are heading. If the outputs settle toward a single value, then that value is the limit. Now, a limit can fail to exist, and it is important to know the common failure modes. The first failure mode is that the function approaches two different values depending on which side you approach from. This leads us to one-sided limits. A one-sided limit describes what happens as you approach from the left or as you approach from the right. If these two one-sided behaviors agree, then the overall limit exists and equals that common value. If they disagree, then the overall limit does not exist. It is worth repeating. A limit exists at a point only when the function approaches the same output value from both sides. If it approaches one value from the left and another value from the right, then there is no single value that describes the tendency near the point as a whole. A second failure mode is oscillation. The function might swing back and forth between values as you approach the point, never settling. In that case, there is no single output value that the function is approaching. The behavior is too restless near the point. A third failure mode is divergence to infinity, meaning the outputs grow without bound as you approach the point. Sometimes this is still described in limit language by saying the function tends to infinity. But it is important to recognize what is being said. There is no finite number that the outputs approach. Rather, they become arbitrarily large in magnitude. Let us also speak about limits at infinity, because they are closely related but conceptually distinct. A limit at infinity describes what the function approaches as the input becomes very large in the positive direction, or very large in the negative direction. This is a way of describing the end behavior of the function. For example, some functions settle toward a horizontal level as inputs grow without bound. Others grow without bound themselves. Others oscillate forever. It is worth repeating this difference. Limits near a point describe local behavior, close to a finite input value. Limits at infinity describe global end behavior, far away along the input axis. Both are limits, but the approaching is of a different kind. Let us pause and reflect. Limits let us talk about approximation in a disciplined way. They let us say, even if we cannot or do not want to evaluate at a point, we can still say what value the function is getting close to. This idea will become essential when we define derivatives, because derivatives talk about what happens as we consider smaller and smaller changes. And it will become essential when we define integrals, because integrals talk about sums of smaller and smaller pieces. Before moving on, let us summarize what we have said about limits. A limit is about behavior near a point, not necessarily at the point. One-sided limits help us analyze behavior from the left and from the right. A limit exists when both sides agree and settle toward a single value. Limits can fail by disagreement of sides, by oscillation, or by unbounded growth. And limits can also describe behavior as the input becomes very large in magnitude, which we call limits at infinity. Now, having limits in hand, we can speak about continuity. Continuity is, in a sense, the promise that near behavior and at point behavior align. Continuity is one of the most comforting properties a function can have. It expresses the idea that small changes in input produce small changes in output, and that there are no sudden jumps or tears in the graph. Formally, continuity at a point means that the value of the function at that point matches the limit of the function as you approach that point. But we will say it slowly, in words, and it is worth repeating. A function is continuous at an input value if, as you move the input closer and closer to that value, the outputs approach the actual output the function assigns at the value. So continuity links three things. The function must be defined at the point, the function must have a limit as you approach the point, and that limit must agree with the function's value at the point. If any of these pieces fails, continuity fails. Let us pause and reflect on the intuitive meaning. If a function is continuous at a point, then the graph can be drawn through that point without lifting your pencil. That is a common mental image. But we should also be careful. Continuity is not just about drawing. It is about predictability. It is about the function not surprising you with a sudden jump. Continuity matters in modeling because many real-world processes are approximately continuous at the scales we care about. Temperature does not usually jump instantly across time, at least not in ordinary settings. Position changes continuously when an object moves without teleporting. Concentrations, pressures, and other physical quantities often change continuously. Even when the real world has discontinuities, continuity is frequently a good approximation, and calculus is often built on that approximation. Continuity also matters because it guarantees the existence of solutions to certain kinds of problems. The clearest and most famous example is the Intermediate Value Theorem. Let us state its idea gently. If a function is continuous on an interval, and if it takes one value at one end of the interval and a different value at the other end, then it must take every value in between somewhere in the interval. In other words, a continuous function cannot skip intermediate output values as the input moves steadily across the interval. It is worth repeating in a more visual way. If you start at one point on the graph and walk along it without lifting your pencil, and if you begin below a certain horizontal level and end above it, then somewhere along the walk you must cross that level. That crossing corresponds to an input value where the function equals that intermediate value. This theorem is a foundational payoff because it connects a purely qualitative property, continuity, to an existence statement. It does not necessarily tell you where the intermediate value occurs. It tells you that it occurs. And that existence guarantee is enough to justify many numerical methods, such as methods that search for roots by repeatedly narrowing intervals. Let us pause and reflect. Continuity is a bridge between local behavior and global conclusions. It takes the idea that a function behaves without jumps and turns it into the certainty that it fills in values, that it crosses levels, and that it cannot teleport from one output region to another without passing through everything in between. Now, it is also helpful to remember that many standard function families are continuous on their natural domains. Polynomial functions are continuous everywhere. Rational functions are continuous wherever they are defined, meaning wherever the denominator is not zero. Trigonometric functions like sine and cosine are continuous everywhere. Exponential and logarithmic functions are continuous where they are defined, with logarithms requiring positive inputs if we are working in the usual real number setting. It is worth repeating, continuity is not always universal, but it is widespread among the functions we study. And where it often fails in recognizable ways, holes where the function is not defined, jumps where two sides disagree, or vertical blow-ups where the function grows without bound. Let us briefly summarize again slowly. Limits describe what a function is approaching near a point. Continuity is the condition that the function's value at the point matches that approaching behavior. Continuity ensures that the graph has no breaks, and it supports existence theorems such as the Intermediate Value Theorem. Let us end by gathering the threads we have been laying down. We began with the big picture. Calculus is the study of change and accumulation. We said, calmly and repeatedly, that there are two master ideas. One is zooming in until behavior becomes essentially linear. The other is adding up small contributions to understand a total. Then we stepped back and gave ourselves the language needed for calculus, the language of functions. We treated functions as objects with a domain of allowed inputs and a range of actual outputs. We emphasized that functions can be represented in many forms, especially through graphs, and we noted that we can transform functions by shifting, scaling, reflecting, and combining. We also introduced inverse functions as reversals that exist only when outputs come from unique inputs. After that, we moved to limits. We emphasized that a limit is about behavior near a point, not necessarily at the point. We spoke about approaching from the left and from the right, about the requirement that both sides agree, and about common ways limits can fail, including disagreement, oscillation, and unbounded growth. We also noted limits at infinity as a way of describing end behavior. Finally, we used limits to define continuity in words. A function is continuous at a point when the value at the point matches what the function approaches near the point. And we explained why continuity matters, both for modeling and for guarantees like the Intermediate Value Theorem, which tells us that continuous functions cannot skip intermediate values. It is worth repeating one last time. Functions give us relationships, limits give us new behavior, and continuity gives us the harmony between new behavior and actual value. These ideas will quietly support everything that comes next, including derivatives and integrals, which are formal ways of speaking about change and accumulation. And with that gentle foundation, we are ready, in the next piece, to begin zooming in more deliberately, and to let the idea of local linearity guide us toward the derivative.